So in this video, we're going to first talk about entropy and what it means and how to do calculations with it. And then next video, we will talk about thermodynamic potentials and how to use them. Okay, now in the textbook by Mr. Wang, there are two sections, 3.1 and 3.2, which we are not going to cover here. Okay, you can read those for yourself if you like. But I think since we're not going to use them, there's not much point in talking about them. So let's look at entropy. Now, entropy is one of those subjects in physics which causes immense confusion both to students and to lecturers, and I don't pretend to be immune from this confusion. The confusion arises from the fact that if you have a state A and a state B, we can in fact calculate the difference in entropy between those two states. We know how to do that now. You just take a reversible path between A and B and you calculate this thing, dq on T, the amount of heat absorbed, divided by the temperature in this reversible path, and you can calculate the entropy difference. So that's SB minus SA if we have a reversible path. And at the same time, we have an idea of entropy which involves disorder. And there's a statistical mechanical way of calculating entropy as well, which we haven't looked at yet. And mapping that onto this particular definition is quite tricky, thinking about how they're actually the same. Okay, and so of course entropy was one of those concepts which, when thermodynamics was being developed, took a long time to figure out what was going on. Okay, so let's the way to think about entropy to start with is like the rest of physics. You try and look at examples, and we know from Clausius' theorem that dq on T, the integral dq on T, is less than or equal to 0 for any cycle, and it's equal to 0 if we have a reversible cycle. Reversible cycle gives equality in this thing. Okay. So whenever you're calculating entropy, even if it's for a process that goes from A to B by some horrible irreversible path, okay, it doesn't matter how you're going between those two states, what you can do is you can always take a reversible path between A and B, okay, where you can calculate the entropy, and that reversible path might be completely different from the irreversible path. Well, in fact, it will be because it's reversible, but it doesn't matter what path you choose. If you start at state A and you go to state B, you can still you can calculate the entropy. Now, you can take a path from A to B which involves some adiabatic cycles, some isothermal cycles, something else, any number of things you want to do going between A and B, and you can calculate the entropy that way. Okay, so let's look, as Wang does, at the isothermal expansion of 1 mole of an ideal gas from a volume V1, like this, to a volume V2. It's isothermal, so it's a constant temperature T. There's a heat reservoir surrounding these things, and so everything is kept at constant temperature. That heat reservoir, you're allowed, of course, with a heat reservoir to exchange heat with it. Otherwise, there wouldn't be any point in having a reservoir. Okay, so it's isothermal. Isothermal, T is constant. Okay, and we're going to expand at constant temperature. So we're going to do it two ways. First way is reversible. So we're going to have a spring here, and that spring slowly compresses, like so, as the gas expands. So that's one way of doing it. And that's clearly reversible. If we do it slowly enough, it'll be reversible. Irreversible is just free Joule expansion. So we just cut a hole here, bang, it expands. Okay. Now they both end up in a volume V2 at a temperature T. Okay, so they're both starting in the same place, this one, and ending in the same place, which is that one. So the entropy change in both those processes of the system here has to be the same of the actual system itself, the gas. Okay. So let's do the reversible state first, the reversible one first, where we go, here's our pressure volume at constant temperature. We start at V1, we go to V2, and we know exactly what's happening along this path because we know PV equals nRT. I think we've got 1 mole in this particular problem. You've got 1 mole, so therefore this N is Avogadro's number, and this N, is 1 mole, and so P is just RT on V, okay, for this expansion. We know exactly what we're doing, okay? Now, both processes have the same initial and final state and the initial and final temperature, and in this particular case, because the temperature is the same, du is equal to 0. Okay, because remember, for an ideal gas, U is the number of moles times CV times T. Okay. However, the two processes are different, and we're going to do the reversible process first. So I'm going to follow this one. Okay, so let's do it. Now, because we know du is equal to 0, we know from the first law that the change in internal energy is the amount of heat absorbed minus the work done. Okay, by the gas. Okay, and because du equals 0, these two things must be equal. Okay, so we don't know what dq is, but we can easily calculate dw. W is the work done by the gas, and it's just P dV. Okay, so there should be a dV here in this integral. Okay, and when you do that from V1 to V2, you just get RT log V2 and V1. Okay, so that's how much heat is absorbed by the gas. Now we also know, and that's also the work done by the gas, same thing, because the energy doesn't change. The entropy change of the gas is really easy because it's just dq on T, the integral of dq on T, and T is a constant because this is done isothermally, so we can take that out the front, just take T out the front, so it's the integral of 1 on T dq, which is 1 on T delta Q, and we just got delta Q from here, and so the change in entropy of the gas is just that. Okay, so that's fairly straightforward as well. We've figured out what the change in entropy of the gas is. Okay. Entropy change of the universe. Now that's more interesting. First, the entropy change of the reservoir. So let's do the entropy change of the reservoir first. The reservoir delivers heat to the gas at constant temperature. So it has an amount of heat sucked out of it, which is equal to this. Okay. So the entropy change of the reservoir is minus dq on the temperature of the reservoir. But the T is constant, so we can take that out. And we just end up with this, which is exactly the negative, of course, of the entropy change of the gas. So the entropy change of the universe, which is the reservoir plus this container, is 0. You add them up and they become 0. Okay, so this kind of calculation looks straightforward again. There's nothing sophisticated in the mathematics, but the logic is what's crucial here. Okay, what's going on? Try and concentrate on the logic, not the actual fact the integral of 1 on V is log V. That's not very exciting. Okay, so we've done that one. We've calculated what the entropy change of the universe is for reversible expansion, and we calculated what the entropy change of the gas is. We know how much heat it absorbs, all that kind of stuff. We can calculate everything if we need to. Now, what about the entropy change of the universe for the free expansion? Okay, now, for a start, we have, for the free expansion, dW equals 0. The gas expands against a vacuum and does no work. Okay, so we know that. Thus, we must have dq equals 0 because we already know du is 0. So we know that du is equal to dq minus dw. We know du is 0. We know dw is 0, so dq must be 0. Okay, so no heat is exchanged between the reservoir and the gas. Okay, all right, so there's no heat expansion, no heat exchanged here. Okay, and because no heat is exchanged, the entropy change of the reservoir must be 0. There's nothing else. The reservoir is not giving up any heat, so its entropy change must be 0. Okay, because ds is dq on T. Okay. Now, ds gas is the same as for the reversible case. Why? Because it's a state function. Remember, the reversible case, we end up with this thing, and we started here. In the irreversible case, we end up with this, and we started here. Okay, and so it's a state function, so the entropy change of the gas must be the same as we had before for the reversible case. So if I asked you, what's the entropy change for this particular process? It's irreversible. What you do is go and try and make up a reversible process, which is what we've done back here, which starts in the same state and finishes in the same state. And we've got that. Okay. So the entropy change for the universe is easy in this case. In the reversible case, it's ds reservoir plus ds gas, which is just ds gas, which is R log V2 and V1, which is greater than 0. Okay, so note here, the entropy change of the whole universe is bigger than 0. Here it's 0. Okay, in the previous case it was 0. Okay. So what went wrong here? Probably wrong is in inverted commas here. Okay, in one case we've got an entropy change of the universe which is positive. In the other case we have an entropy change of the universe which is 0. Okay. So what happens here? The irreversible free expansion involves an increase of the entropy of the universe of that and a loss of work equal to RT log V2 on V1, which is T delta S universe. Remember, in this particular case, for the reversible case, where are we? Back here, we did some work against the spring. The spring stored some energy. It stored that much. Okay, we stored some energy in the spring. We did some work. Okay, in the reversible case, we basically just stuffed up entirely. We didn't store any energy. We didn't do any work. And we've lost this work. Well, how much work have we lost? We lost a work which is this, we know, and that turns out to be T delta S universe. And as Wang says, the increase in total entropy is a reflection of the loss of useful energy. We've done this ridiculous process where we just allowed the gas to expand without doing any work. That was a serious error because now we've lost the ability to do work. Okay, and we're not going to get it back. Whereas in the reversible case, what happened is we compressed this spring, and the spring can then be used to do some work somewhere else, to run an engine, for example, or to recompress the gas if we wanted to. Okay, so that's a sort of complicated example, not a complicated one, but it's one involving compression of gases, where you can calculate entropies and you can see what happens. Okay, and it's very important to go through that particular problem and see if you understand exactly what's happening. Again, I emphasize the maths is trivial, but the logic, the calculation is not trivial. Okay, so let's do another even simpler example. And this is heat conduction. Now, we will go through heat conduction later on, but you already know about heat conduction. You have a hot brick here at temperature T2, a cold brick at temperature T1, which is less than T2, and you might have some sort of piece of brass or something here which connects the two, and heat flows from the hot brick to the cold brick through the brass. Okay, so let's assume the brass doesn't absorb much heat. It's just a conductor of heat. It has no zero heat capacity. So heat conduction from a reservoir at temperature T2 to one at T1 involves an increase of entropy. Why does it involve an increase in entropy? Well, because this particular object here, when there's an amount of heat Q flowing to it, it has an increase in entropy of Q on T1. And this brick, which is hot, minus Q leaves it at temperature T2. Okay, so the entropy change is what we've got here. And because T1 is less than T2, the entropy change is bigger than 0. Okay, so Q leaves 2 and goes to 1. And basically what's happened is the entropy change of the universe is this in this thing, and it's bigger than 0. And what's gone wrong here? Well, wrong in inverted commas, but what's happened is this heat, which you've lost out of here and went to here, could have been used to generate work via a Carnot engine or something like this, but it's been wasted. Okay, and that waste is reflected in this increase in entropy there. Okay, so that's a couple of examples of using entropy and what happens when you have systems which are irreversible. Entropy increases. So Huang introduces this entropy-temperature diagram, which sometimes can be useful in calculating things. So we plot temperature here versus entropy for a cycle. Now in this case we know that we've got a Carnot cycle, which has two adiabats here and here. These are the two adiabats, constant entropy, and two isotherms, constant temperature. And of course that means on an entropy-temperature diagram that you will get a rectangle. Okay. Now, we can easily work out what the efficiency of this particular Carnot engine is just from the diagram, okay? Because we know the work done is A, it's the integral over here, okay? You can figure that out yourself. And the heat added is just this area here, the whole area here, because it's it's, you know, the multiples of delta S times delta T. Okay, and so what we have here is a formula for the entropy, not the entropy, sorry, the efficiency, which is that. Okay, so you go through that yourself and figure out what's going on. But the heat rejected is B. Okay, because that's the heat rejected here. Okay, so that's the heat added is A plus B. The work done is A, and we end up with this formula. Okay, so go and convince yourself that that's the right formula for the efficiency. Now, you can take more complicated cycles which are not Carnot cycles and break them up into Carnot cycles. So this one, for instance, you can break up like that, okay, because this section of thing here basically cancels. You've got one going down, one going up, and they'll cancel out. So anything you can break up into Carnot cycles. You can even break up something which has curved sections just by doing lots and lots of infinitesimal Carnot cycles. So the Otto cycle you can break up into Carnot cycles as well. On the temperature entropy diagram, you can draw the Otto cycle and calculate the efficiency by looking at all the different little Carnot cycles if you wanted to. All right, so that's the end of our discussion of entropy. We still haven't really solved the mystery of it, but now you're at least more familiar with how to use it for different calculations.